Today, we're going to look at an overview of Kerberos Authentication. This is not SAS specific and just looks at Kerberos in general. In this session, we will introduce the different components of Kerberos and take a first look at the different messages transmitted as part of a Kerberos Authentication exchange. I'm Stuart Rogers with SAS, and this is the Technical Insights and Expertise series. Let's start by listing the components we will be considering for this overview of Kerberos Authentication. First, we have the Kerberos Key Distribution Center, or KDC. On the KDC, we have two separate services running. The first is the authentication service, and the second is the ticket granting service. We will not specifically call out one operating system over another, or one Kerberos implementation over another. Throughout, we will try to be as generic as possible. Next, we have the client, where our end user is located. This could be an actual client PC, or another server where the client process is running. Finally, we have the server, where the server process the end user on the client wants to connect to. So here we have the three heads of the Kerberos protocol: the KDC, the client, and the server. The next part of our overview is to talk about keys. Kerberos relies upon strong encryption, and for the encryption to work, we need to have keys used by those encryption algorithms. We have two different groupings of keys. The first grouping of keys are long-term keys. As the name suggests, the lifetime of these keys is relatively long-term. These long-term keys are synonymous with passwords. The other grouping are session keys. And as the name suggests, these session keys are short-lived and unique to each session. Within the long-term keys, we have the long-term key for the ticket granting service. This is associated with the password for the account running the ticket granting service on the KDC. The service long-term key is a key associated with the service the end user is going to connect to. Again, this is associated with the password of the account or object representing the service in the KDC's database. Finally, for long-term keys, we have the key associated with the end user. This is associated with the password of the end user in Kerberos. For session keys, we first have a session key specific to our end user's connection to the service. This service session key will have a short lifetime and will be unique to the individual end user's connection to the service. Our final key is the ticket granting service session key. Again, a short-lived key, this is associated with the end user's individual connection with the ticket granting service. In the next sections, when we look at the messages involved in Kerberos authentication, we will see how the different keys are used to encrypt messages sent between the three heads of the Kerberos system. Whilst Kerberos uses strong encryption on the content of the messages, the names of the messages in the next section can be seen in a network trace. This can be useful for troubleshooting Kerberos authentication issues, as it allows you to understand how far the process has gone before running into problems. The first set of messages we will consider are those used to carry out the initial authentication of the end user. The Authentication Service Exchange. The KRB AS request is the request sent to the authentication service running on a KDC when a Kerberos principal, our end user, initially authenticates. The KRB AS request message can contain an optional authenticator. This is not required, but is specified by the authentication service with a pre-auth required message in response to an initial attempt to authenticate. If the authenticator is required, it will contain several pieces of information and normally a timestamp from the client machine. The content of the authenticator is encrypted using the long-term key of the user. The message is created and encrypted by the client machine. The content is then decrypted by the authentication service running on the KDC. This means the authentication service must have access to the same long-term key for the user to be able to successfully decrypt the message. By using the same key to encrypt and decrypt the message, we ensure that both parties have access to the same long-term key without having to send the long-term key across the network. The response sent by the authentication service is a KRB AS response. Within the response is a copy of the session key the client will later use in communications with the ticket granting service. This is encrypted with the user's long-term key. The second part of the response is the ticket granting ticket. The idea for the ticket granting ticket is that this will be used for all subsequent requests to authenticate to specific services. The TGT includes information about the end user, as well as a second copy of the ticket granting service session key. All this information is encrypted with a different long-term key. This time, the long-term key of the ticket granting service is used to encrypt the content. The authentication service on the KDC encrypts the TGS session key with the user's long-term key, which means the client which has access to the user's long-term key is able to decrypt the message and extract the ticket granting service session key. Since this is encrypted with the user's long-term key, no one else is able to extract this session key. Equally, the authentication service creates the TGT and encrypts this with the long-term key of the ticket granting service. The difference here is that the client cannot decrypt the ticket granting ticket. Only the ticket granting service will be able to decrypt the TGT and get at the content. So in the response, we have two pieces of information, and only one of those is accessible to the client. The second, the TGT, is kept encrypted by the client for later use. Now, the initial authentication can take place at any time and does not have to be directly related to the next set of messages. The ticket granting service exchange is a request and response sent between the client and the ticket granting service on the KDC when an already authenticated principal, or end user, wants to authenticate to a service. The initial request for this is the KRB TGS request. As before, the first part of the message is an authenticator, including information about the end user and often a timestamp from the local client. Notice this time the authenticator is encrypted with the ticket granting service session key that the client received in the previous KRB AS response, so the end user's long-term key is not used this time. The second part of the request is the copy of the TGT. Since the client was not able to decrypt this, this is sent exactly as the client received it in the KRB AS response. The authenticator is encrypted by the client, which holds a copy of the ticket granting service session key. It gets decrypted by the ticket granting service running on the KDC. Remember, it was the authentication service that encrypted the ticket granting ticket. And the ticket granting service is then able to decrypt the ticket granting ticket using the long-term key of the ticket granting service. Strictly speaking, the TGT is decrypted first by the ticket granting service so that it can extract the ticket granting service session key from within inside the TGT. The TGS session key is thus extracted and is then used to decrypt the authenticator sent by the client. This means that the ticket granting service does not need to keep and maintain a collection of those session keys. Each time it needs to use a session key, it can obtain it from within the TGT. This also means that the KRB TGS request can be sent to a different KDC to the one used for the initial authentication. The response sent by the ticket granting service is the KRB TGS response. Within the response sent to the client is another session key. This session key will be used with the service the end user wants to authenticate to. This service session key is encrypted with the ticket granting service session key. Also in the response is the service ticket the end user will use to authenticate to the service. This is encrypted with the long-term key of the service. So, like the TGT, the client is unable to decrypt the content of the service ticket. The service session key is encrypted with the ticket granting service session key by the ticket granting service, which can then be decrypted by the client, which holds a copy of the same ticket granting service session key. The service ticket is also encrypted by the ticket granting service. but can only be decrypted by the service and not the client, since the client does not have the long-term key of the service. Using the service long-term key to encrypt the service session key inside the service ticket ensures only the specified service will be able to decrypt the service ticket and means the service does not need to communicate directly with the KDC. Until now, all the communication has been between the client and the KDC. Now we'll look at the Kerberos message exchange between the client and the server hosting the service the end user needs to authenticate to. In the Kerberos protocol, the request from the client to the server is a KRB AP request. As with the other requests, this KRB AP request contains an authenticator, which along with other content may contain a timestamp. This time, the authenticator is encrypted using the service session key. Remember, this was provided to the client in the KRB TGS response. Also, the client sends the service ticket obtained in the KRB TGS response. The client is not able to decrypt the service ticket since this is encrypted using the long-term key associated with the service. So, it's the client that encrypts the authenticator, which will then be decrypted by the service they connect to. The service ticket was encrypted by the ticket granting service and can only be decrypted by the correct service. Just like the TGT we looked at before, the service ticket is decrypted first using the long-term key of the service. This allows the service to extract the service session key from within the service ticket and use this to decrypt the authenticator. If you are looking at a network trace of the Kerberos messages, you are unlikely to see the KRB AP request message being sent by the client to the server. This request is most often wrapped inside the protocol being used by the client to connect to the service. This might be the GSS API protocol, for example, with something like Kerberized SSH, or Spinago for a web application. The Kerberos protocol defines an optional response from the server to the client. This optional response allows for the mutual authentication of the service to the end user. In the Kerberos protocol, the optional response is the KRB AP response message. The message only contains an authenticator encrypted with the service session key. As with the other authenticators, this can include a timestamp from the server hosting the service. The authenticator is encrypted by the service since this has access to the service session key after having successfully decrypted the service ticket. It is decrypted by the client since this also has the service session key from the KRB TGS response. This allows the client to know that the service was the correct service to send the service ticket to, since the service was able to extract the session key and use it to encrypt the authenticator. Again, if you're looking at a network trace of the Kerberos messages, you are unlikely to see this optional KRB AP response message being sent by the server to the client. As before, this response is most often wrapped inside the protocol used by the client to connect to the service. This completes our overview of Kerberos authentication. In our next session, we will look at different process flows showing how these message exchanges used in the Kerberos protocol are put into action. For further information, you can see the following resources. The Kerberos protocol version 5 is defined in RFC 4120, available here. The GSS API protocol is defined in RFC 4121, available here. And Microsoft have a great guide explaining how Windows implements Kerberos, available here. Hopefully, this has given you a good overview of the messages and use of encryption within the Kerberos authentication protocol. I hope this will be of use to you if you need to troubleshoot issues with Kerberos. Remember, the encryption algorithms used in the different parts of the messages are exchangeable, so it's important that the different parties are using algorithms that both sides can process. Also, since the authenticators seen in most requests often include a timestamp, ensure the system time is synchronized across all parties Today we're going to follow on from our previous Kerberos overview and look at Kerberos Authentication in more detail. We're going to examine the messages passed between components and how different encryption keys we reviewed last time get used in practice. We will look at both the initial authentication of the user and how the user then authenticates to a service. I'm Stuart Rogers with SAS, and this is the Technical Insights and Expertise series. First, we will look at the process of authenticating the user. From last time, the messages here are the KRB-AS request and KRB-AS response. We start with the client machine and the KDC. Running inside the KDC are the authentication service, labelled AS, and the ticket granting service, labelled TGS. The first step is for the user to provide the client machine with their long-term key. Remember, this is associated with the password of the user. So, the user types their password into the client, or perhaps inserts a smart card, or provides a biometric. The client sends a clear text message of the user ID to the authentication service running on the KDC. This is the KRB-AS request. Ideally, the authentication service then responds with an error. It tells the client that it needs to pre-authenticate. So the error it sends back is that pre-auth is required. The client then takes the user's long-term key and uses this to encrypt an authenticator. As we discussed last time, the authenticator quite often includes a timestamp from the client. This authenticator, A, is now sent to the authentication service. The KDC looks up the user's long-term key and uses this to decrypt the authenticator, A. Normally, this step will include comparing the timestamp to ensure that this is not an attempt by an attacker to replay a valid authenticator. Decrypting the authenticator A with the user's long-term key validates the user. With the user validated, the authentication service constructs two pieces of information to be sent back to the client. First, it generates a session key for the ticket granting service. Remember, the session keys have a short lifetime. This session key is then encrypted using the long-term key of the user, shown as B on the diagram. The other piece generated is the ticket granting ticket, C. Information in the TGT is encrypted with the long-term key of the ticket granting service, meaning that the client is unable to decrypt the TGT since it does not possess the correct long-term key. One of the important parts of the TGT is the same ticket granting service session key that was encrypted using the user's long-term key. So essentially, the TGS session key is sent in two different formats to the client. One format the client can access, the other the client cannot access. This will become important later when the TGS session key is used. Finally, the client uses the long-term key of the user to extract the ticket granting service session key from the KRB-AS response, B. One thing to note is that it is possible to disable pre-authentication. In such a case, we skip steps 3, 4, and 5. This removes some of the security provided by Kerberos and just leaves us relying on the fact that only a client with the user's long-term key will be able to extract the ticket granting service session key from the authentication service response. It is not recommended to disable pre-authentication. This completes using Kerberos to authenticate the user. Once the user has successfully authenticated to the authentication service running on the KDC, at some point in the future, they are then able to attempt to authenticate to a service. Now, we show all three heads involved in the Kerberos authentication protocol. We have the client with the end user, the server running the service the end user wants to connect to, and the trusted third party in the form of the Kerberos Key Distribution Center. Our Kerberized client is aware that for it to make a successful connection to the Kerberized server, it must request a service ticket from the KDC. This is a KRB TGS request and KRB TGS response set of messages. The client constructs the KRB TGS request message to request the service ticket from the ticket granting service running on the KDC. Included in this request is an authenticator A and the ticket granting ticket B. This time, the authenticator A is encrypted using the ticket granting service session key. As before, normally this authenticator will include a timestamp from the client machine. When the ticket granting service receives the request, it uses its own long-term key to extract the ticket granting service session key from the ticket granting ticket B. Then, it uses the extracted TGS session key to decrypt the authenticator A sent by the client. As before, normally this includes a timestamp which the ticket granting service can compare to its current system time. This limits the chance of an attacker replaying a valid authenticator. Decrypting the authenticator with the TGS session key extracted from the TGT-B does two things. First, it validates the user. But also, since the TGS session key was sent in the request, it means that the ticket granting service does not need to keep track of session keys. So, essentially, from this perspective, the ticket granting service is stateless. It does not matter if this request for a service ticket is sent to a different KDC in a cluster to the initial authentication of the user. With the user validated, the ticket granting service is able to send the KRB TGS response. Included in the response is a session key for the service, which is encrypted, again, with the ticket granting service session key, shown as C, as well as the service ticket D. The service ticket D also contains a copy of the session key for the service, but the service ticket D is encrypted with the long-term key of the service, so the client will be unable to process the contents of the service ticket, since it does not possess the service long-term key. The client takes the part of the KRB TGS response containing the encrypted version of the service session key, shown as C. The client then uses its copy of the ticket granting service session key to extract the service session key from the message. Now that the client has both the service ticket and the service session key, it can send its authentication request to the service. This is the KRB AP request message. Contained in this message is the service ticket D and a new authenticator E. This time, the authenticator is encrypted with the service session key. Remember from last time, when looking at the network traffic, you may not see the KRB AP request message, as this is often wrapped inside the protocol used to connect to the service, such as the GSS API or Spinago. The Kerberos service then performs an action similar to that performed by the ticket granting service to validate the user. The service takes its long-term key and decrypts the service ticket. This gives the service access to the service session key created by the ticket granting service. With this session key, the service is then able to decrypt the authenticator sent by the client and validate the user. As before with authenticators, these usually contain a timestamp to mitigate replay attacks. The last two steps are defined in the Kerberos protocol as optional. The service can send a KRB AP response containing another authenticator. This authenticator is encrypted using the service session key. When the client receives the optional response, it can use its own copy of the service session key to decrypt the authenticator. If the client is able to use the session key to decrypt the authenticator, it proves the same session key was used to encrypt it. This in turn means the service was able to correctly decrypt the service ticket the client sent, and hence the client is assured the correct service was sent the service ticket. This completes our overview of Kerberos authentication. In the next session, we will look at some more advanced authentication processes, namely both delegation and cross-realm authentication. For further information, you can see the following resources. For a definition of the Kerberos protocol, you can see RFC 4120 available here. And for a definition of the GSS API protocol, you can see RFC 4121 available here. And finally, Microsoft have published a great guide explaining how Windows implements the Kerberos protocol, and you can find that here. Hopefully, this has given you a better understanding of how the different Kerberos tickets and encryption keys are actually used. Having this understanding should make it easier for you to troubleshoot issues with Kerberos authentication. Today, we're going to follow on from our previous two Kerberos authentication sessions and look at some more advanced topics. If you have not reviewed the previous two sessions, I strongly suggest you view those first. In this session, we will examine Kerberos Delegation and Kerberos Cross-Realm Authentication. I'm Stuart Rogers with SAS, and this is the Technical Insights and Expertise series. The first advanced case we will consider is that of Kerberos Delegation or forwarding. In an Active Directory Microsoft world, this technology is referred to as delegation, whilst MIT Kerberos refers to forwarding authentication. The principle with this setup is that the service the end user wants to authenticate to is going to reuse the end user's credentials to connect on to a second service. An example of this setup would be using Kerberos to authenticate to the SAS middle tier and having your credentials forwarded onto the server tier to start a workspace server using Kerberos. This requires that the first service in Active Directory terminology is trusted for delegation. So, in this case, as before, we have the KDC running the authentication service and ticket granting service, the client machine with the end user, and the first server running a service. But now we introduce a second server running a second service. We want to have our end user credentials propagated from the first service onto the second service. The initial authentication of the end user has already taken place. If you want to review that process, please have a look at our last session. The first step is similar to when we authenticated to a service previously. The Kerberos client constructs the KRB TGS request, including the end user's ticket granting ticket, B, and an authenticator, A. The ticket granting service running on the KDC takes its own long-term key and uses this to decrypt the TGT, B, sent by the client. This allows the ticket granting service to extract the ticket granting service session key. The TGS session key is then used to decrypt the authenticator and validate the end user. The ticket granting service then builds the KRB TGS response containing both the service ticket D and a service session key encrypted with the TGS session key shown as C. This service ticket and the service session key are both for the first service. When the client receives the KRB TGS response, it takes the encrypted service session key, shown as C in the diagram, and decrypts this using the client's version of the ticket granting service session key. This gives the client access to the service session key for the first service. Now, the client sends a second KRB TGS request. In this second request, the client requests a forwardable ticket granting ticket from the ticket granting service. The second request, like the first, contains the TGT, shown as B, and another authenticator, shown again as A. Just like with the first KRB TGS request, the ticket granting service uses its long-term key to decrypt the session key from the ticket granting ticket. Then it uses the session key to decrypt the authenticator and so validate the user. The response the ticket granting service sends to the second KRB TGS request is slightly different. This response, shown as step 9, contains a new second ticket granting service session key encrypted with the first ticket granting service session key, shown as E, and a forwarded ticket granting ticket, F, which contains the second ticket granting service session key. When the client receives the second KRB TGS response, it takes the encrypted second TGS session key, shown as E, and decrypts it with the first session key it already has. So now the client has access to both the ticket granting service session keys and the two ticket granting tickets, the original TGT and the forwarded TGT. Now, in step 11, the client connects to the service with a KRB AP request. Remember, this is most likely wrapped inside the protocol used to connect to the service, such as GSS API. In this request, the client sends the service ticket D and an authenticator encrypted with the service session key G. The first service uses its long-term key to decrypt the first service ticket D and extract the service session key from that service ticket. This service session key is then used to decrypt the authenticator G and validate the user. As in our last session, there is an optional reply the service can send to the client, the KRB AP response, which contains an authenticator, this time encrypted with the service session key, shown as H in the diagram. When or if the client receives the service's authenticator H, it can use the service session key to decrypt the authenticator and so validate the service. Either after the optional KRB AP response or after sending the initial KRB AP request, the client sends the forwarded TGT F and an encrypted copy of the second TGS session key, shown as I, to the service in a KRB cred message. The TGS session key is encrypted using the service session key shared between the client and the service. Just as with the KRB AP request and response, this is most often wrapped inside the protocol used to connect to the service. Upon receiving the forwarded TGT, shown as F, and the encrypted TGS session key, I, the service uses the service session key to decrypt I and obtain the TGS session key. So now the service has the forwarded ticket granting ticket, shown as F, and the associated ticket granting service session key. For the first service to make a Kerberized connection to the second service, it needs to request a service ticket for the second service from the ticket granting service running on the KDC. So the first service sends a KRB TGS request containing the forwarded TGT F and a new authenticator J encrypted with the TGS session key associated with the forwarded ticket granting ticket. As before, the ticket granting service decrypts the ticket granting ticket, shown as F, using its long-term key. From this, it obtains the associated ticket granting service session key, which is then used to decrypt the authenticator and so validates the end user, but this time from the first service. The ticket granting service response, KRB TGS response, sent back to the service contains a service ticket for service 2, shown as L, and the second service session key encrypted with the ticket granting service session key from the forwarded ticket granting ticket, shown as K in the diagram. Upon receiving the KRB TGS response, service 1 uses the ticket granting service session key it has to decrypt K, and from that extracts the session key associated with service 2. So now the first service has the forwarded ticket granting ticket F and its associated ticket granting service session key, and the service ticket for the second service L and the session key associated with this service ticket. So in step 23, service 1 connects to service 2 by sending either a KRB AP request or by using the protocol used to connect to service 2. Contained in this request is the service ticket for service 2, shown as L, and a new authenticator encrypted with the service session key for service 2, shown as M in the diagram. For service 2 to validate the user, it takes the second service ticket, L, and decrypts it using its long-term key. This gives service 2 the session key for service 2, which is then used to decrypt the authenticator M and so validate the user. As before, we have an optional step for service 2 to validate itself to service 1. For this to happen, service 2 can send an authenticator N encrypted with the second service session key back to service 1. Finally, service 1 uses the service 2 session key to decrypt the authenticator N and so performs the optional validation of service 2. So we can see the process of Kerberos delegation or forwarding credentials is quite complex. And in this case, the first service now needs to be able to make the authentication request on behalf of the end user and so make connections to the KDC. The second advanced topic we will address is cross-realm authentication. For cross-realm authentication, the client and server are in different Kerberos realms. Outside the process of authentication we will go through here, the administrators of the environment need to correctly configure a cross-realm trust for this process to work correctly. To start with, we have our standard 3 heads of Kerberos authentication: the client with the end user, the server running the service, and the KDC. For cross-realm authentication, we then have an additional KDC for our second Kerberos realm. As with the previous section on delegation, the initial authentication of the end user has already taken place. First, the Kerberos client makes a request to its defined KDC for a service ticket. This is the standard KRB TGS request message containing the ticket granting ticket B and an authenticator A encrypted with the TGS session key. As normal, the ticket granting service decrypts the ticket granting ticket B using its long-term key to extract the ticket granting service session key. The ticket granting service then uses the TGS session key to decrypt the authenticator A to validate the user. Now, the ticket granting service looks for the service principal name in the request and discovers that this SPN is not in its realm. So, the ticket granting service sends the reply KRB TGS response containing 2 items, C and D, where D is a ticket granting ticket for realm 2, including information about the client, and a ticket granting service session key for realm 2. This TGT is encrypted using the long-term key of the shared cross-realm principal. And C is the ticket granting service session key for realm 2, encrypted using the ticket granting service session key associated with the initial ticket granting ticket obtained by the client. The client decrypts C using its initial ticket granting service session key to obtain the TGS session key for realm 2. Now that the client has a TGT and associated ticket granting service session key valid for the second realm, it is able to create another KRB TGS request for the KDC in the second realm. This is shown in step 6 and contains the TGT for realm 2 and an authenticator encrypted using the TGS session key for realm 2. As we've seen previously, the ticket granting service, this time on the second KDC, takes the ticket granting ticket, uses the long-term key to decrypt the ticket and extract the session key. The difference here is that the long-term key used is associated with the cross-realm trust rather than the ticket granting service long-term key. Once the ticket granting service has the ticket granting service session key, it can decrypt the authenticator E and validate the user. The ticket granting service on the KDC in realm 2 sends the KRB TGS response to the client containing the service ticket F encrypted with the service long-term key and a service session key G encrypted with the cross-realm ticket granting service session key. Once the client receives the KRB TGS response, it takes the encrypted service session key G and decrypts this using the ticket granting service session key associated with the cross-realm ticket granting ticket, which gives the client access to the service session key. As before, the KRB AP request the client sends to the server most often is wrapped inside the protocol the client uses to connect to the server. Within this message is the service ticket from the KDC in realm 2, shown as F, and a new authenticator encrypted with the service session key, shown as H. The service goes through the standard steps to validate the user, namely taking the service ticket F and decrypting this with its long-term key to obtain the service session key. With the service session key, the service can then decrypt the authenticator H and validate the user. Then we show the optional KRB AP response, which contains an authenticator I encrypted with the service session key by the service and sent to the client. The client can then decrypt the authenticator I using the service session key to optionally validate the service. This completes the example of cross-realm authentication. The key parts of this setup are the cross-realm long-term keys shared by the two realms. The creation of these long-term keys is part of configuring the cross-realm trust we mentioned at the beginning. It's also worth noting the client needs to communicate with both the realms to correctly obtain the service ticket. If there are limitations on this network connectivity, cross-realm authentication is not going to work. This completes our review of advanced Kerberos authentication. For further information, you can see the following resources. To see details on the Kerberos Protocol version 5, you can review the RFC 4120 available here. And to look at the GSS API protocol, review RFC 4121, which you can find here. Finally, Microsoft have a guide explaining how Windows implements the Kerberos protocol, and that's available here. I hope you now have a better understanding of how the Kerberos tickets and encryption keys are used with these more advanced setups. By presenting these process diagrams, I think it makes these advanced setups clearer to follow and hence easier to troubleshoot any issues you might be having. Thank you, and check back with your global enablement and learning team for more technical insights.